Today we will be discussing periodic trends. We do not need to do the whole periodic table because the transition metals and intertransition metals have other properties that causes the trend not to work out exactly the same way. So we will be working on our representative elements, so the elements that have a Roman numeral with the letter A in their title above the line. We will be using a simplified periodic table, removing both the transition metals and the intertransition metals. Our first trend is atomic radius. Atomic radius is the distance from the center of the nucleus to the outermost valence electrons. So there's a measurement from the center of the nucleus to the outermost valence electrons. So let's start with hydrogen. Hydrogen with 1 proton and 0 neutrons. If it is neutral, it'll have 1 electron. That electron will be found in the first energy level. How do I know the energy level? Well, on the periodic table, the periodic or period number is the number of energy levels that an element in that period will have. No matter what element you're at, if you're in that period, that's how many energy levels you will have. Often your outermost electrons will be found in that energy level as well. So hydrogen, being in period 1, will only have 1 energy level. Being number 1, it'll only have 1 electron and 1 proton. So what happens when it gets bigger? When we go to helium. Helium has a mass of 4. So in order to become helium, it had to gain 1 proton and 2 neutrons. So we're getting a lot of mass added to the center of the nucleus. This mass creates a directional gravitational pull. Oops, this is backwards. It creates a directional gravitational pull. I'm adding a lot of mass to the nucleus and virtually 0 mass to the ring, so that energy level gets pulled closer and closer to the nucleus. So as I go from left to right on the periodic table across a group, the rings or the energy levels become more contracted to the nucleus because of that directional gravitational pull. Our next element, lithium, number 3 on the periodic table, has a mass of 7, so it's going to have 4 electrons on it. But it's an energy level 2. So let's compare. Hydrogen is in group 1, period 1. Lithium is in group 1, period 2. What happened to the atomic radius? Well, as you move down on the periodic table, as we stated before, the period number is how many energy levels it has. So being in energy level or period 2, it has 2 energy levels. It has a newer energy level outside of the previous one. If there's a newer energy level outside of the previous one, it's obviously going to get a little bit bigger. Let's keep moving down group 1. Our next one down group 1 is sodium. Sodium has 11 protons and 11 neutrons to give it that 22 mass. And it has 3 energy levels where the electrons will be found. New energy level outside of the previous one causes it to become bigger. So as you move down, there's a trend happening. Last one that we're going to talk about would be potassium. Potassium is in group 1, but it is in period 4, so it has 4 energy levels. So as I'm moving down the periodic table, my atomic radius increases because I'm adding a new energy level outside of the previous one. So from top to bottom, down a group, the atomic radius will increase. So let's draw this in on our periodic table. On your periodic table project, should your class be doing it, it requires that you write the nuclear charge. So what is the charge of the nucleus? Well, the only particle in the nucleus that has charge is the proton. So all we're writing would be +1 for hydrogen, plus 2 for helium. We'll do a plus 3 for lithium, plus 11 for sodium, and plus 19 for potassium. And we're going to go across, so we're going to do plus 4, plus 5, plus 6, plus 7, plus 8, and plus 9, and plus 10. All right. Why did I put all these on there? Because on your periodic table project, it wants you to go down group 1 and across period 2. You have to show all of these. So hydrogen has 1 energy level. Helium also has one energy level, but it's going to be a little bit smaller than the hydrogen is. The second row or period is going to have 2, but as they move across, that gravitational pull is going to increase. So these energy levels are going to be getting closer and closer to the nucleus. Now, as we're going down, we're going to add new energy levels outside of the previous one. So that one had 2 above it, so this one has 3. And this one has 4. So this is atomic radius. I repeat, as you go across a period, the gravitational pull, directional gravitational pull, pulls the electrons closer to the nucleus because I'm adding a lot of mass to the nucleus and virtually 0 mass to the energy level. The electrons have virtually 0 mass. So from left to right, atomic radius decreases. From top to bottom down a group, I'm adding a new energy level each step down, which means since that new energy level is outside of the previous one, my atomic radius increases going from top to bottom. This is really, really important because we have 2 more types of trends that we wanted to discuss, and the other trends are dependent upon the size. The first trend we want you to write down is electronegativity, which is the energy the nucleus exerts over the outermost or shared electrons. Electronegativity is the energy the nucleus exerts over the outermost or shared electrons. So what does that mean? Well, what it means is I have electrons in my rings. The rings are showing me the location outside of the nucleus. Well, the nucleus has to exert force over them to hold them close to, like, into a bond with that atom to make sure the atom stays the same. Well, the nucleus will exert the most force over the ones closest to it. The further the electrons are away from the nucleus, the less it has the ability to control it. They're further and further away. It's like if you have a pillow and you're holding it in your arms, you have a lot of control because it is very close to you. But if it's across the room on the couch, you have virtually no control because it's so far away. So what I'd like you to see is our comparison here. These are both in group 1A. This is hydrogen, this one is potassium. So potassium is much bigger. Its electrons are much further away. In a previous lab you did, you were trying to discover the reactivity down this group. Doesn't it stand to reason that if an electron is really close to the nucleus, as easy as it might be for it to go away, it's still going to be harder than it would be for an electron on the fourth energy level so far away from the nucleus? If the nucleus is exerting force over the outermost electron and it's really, really far away, would it be easier or harder to take those electrons away, the one that's furthest away? In group one, there's only one in the outer shell. Would it be easier to take an electron from close to the nucleus or one that's farther away from the nucleus? This is a trend known as ionization energy, which is the energy required to remove the outermost electrons. Ionization energy is the energy required to remove the outermost electrons. So what you should notice is that if I'm really close to the nucleus, my nucleus can exert more force over the electron. If it's exerting more force over the electron, it would take more energy to take it away. So the higher the electronegativity, the higher the ionization energy would be. So these trends, while they're not really the same trend, they follow the same pattern. That's our key. They're different trends. They're actually opposite trends. The electronegativity is trying to hold on to electrons, where ionization energy is trying to take them away. So since those trends have the same pattern, then we have to look at it in relation to the other pattern. We know from top to bottom that the atomic radius is going to increase. We went from top down to number 4 here. As it increased, the electronegativity, the amount of energy the nucleus can exert over the outermost electrons, decreases because they're further and further away. If the amount of energy the nucleus can exert over the outermost electrons is decreasing, that means it would take less energy to take those electrons away, which means they become more reactive. If it's easier to take the outermost electrons away, they become more reactive, which is why in our experiments we learned that potassium is far more reactive than lithium, than sodium. Because its outermost electrons are further away, it was easier to take them away, they become more reactive. Okay, top to bottom, atomic radius increases, which means from bottom to top, ionization energy and electronegativity will increase. It's the opposite effect. So as atomic radius decreases, ionization energy and electronegativity increases. Going from left to right across a group, the atomic radius decreases due to that directional gravitational pull. So from left to right on the periodic table, the trend is that ionization energy and electronegativity will increase. You should notice that as I'm going up and right, I'm going to get the highest level of ionization energy and electronegativity. But it stops right here at F. The reason why we say the electronegativity and ionization energy stops at fluorine is because of that definition. Electronegativity is the amount of energy over the outermost or shared electrons. This column are noble gases. They don't share their electrons. They are non-reactive. They don't share them. So we don't look at that as electronegativity. Does it have a force controlling its electrons? Absolutely. But since it's not forming a bond, it's probably has another name which we don't need to know. Since it also does not lose electrons or gain electrons, ionization energy is not accounted for in the noble gases. So when you're doing your projects, make sure you remember, do not include the noble gases, because noble gases do not form bonds. Therefore, we do not look at electronegativity or ionization energy for the noble gases. We stop at fluorine, which is why the project requires that you specifically label fluorine. It is the highest electronegative, highest ionization energy element on the periodic table.